be doing symbolic factoring today. Since the last time that we streamed, I actually worked on the integration of SymPy. I tweeted that yesterday. And basically, what I've done is I've integrated SymPy in a way that now basically you can create. Let me show you. Notebooks testing. So you can basically now create a hypergraph that doesn't start with a predefined or well-defined state, but rather with a symbolic state. And by symbolic, it might be the wrong naming, but by symbolic, what I mean is that instead of having a qubits in the zero state, you have qubits that are basically in a unknown pure state, right? So basically, that's the way it looks like. So you have this coefficient in here, which is a complex coefficient, and you evolve the rest, and as you can see, you have your final state here, and then of course you can't resolve that. Like you need to resolve that in order to know. So you can resolve. The idea is which is still not implemented, but you just go and say, look, I can give initial values to the stuff, to the coefficients, and then I can see what's the state that I end up with, right? And I can play. You can eventually play with this as well, or you could just play with algorithms symbolically to kind of, for example, teleportation. See that the coefficients, like if you're trying to see whether you can teleport these coefficients down to another state's coefficients, you can see that without actually having to play with concrete values. So that's the idea. But this is all good and done, but what's not done is the factoring part of these. It doesn't handle that yet, right? So you can create a node, you can create a hyper edge, also not from a state vector yet. That is something that I still have to refactor, but it shouldn't be a big deal. But it's probably an off-stream kind of work, so it's not so much interesting. And basically the rewrite works, but what I haven't really tested properly is whether this is actually working correctly, for example, right? Like I am not so sure that these things work correctly in terms of like I still think that these coefficients here should somewhat be normalized. And I really don't know how to approach this. That's a question that I want to try to answer today, right? In terms of these, and then take a look at the factoring. Maybe that should be the starting point. See how can we factor, let's start with a simpler example, right? So insert cell above, and I'll just go with a 1 qubit symbolic system, and I will. What I will do is I will just just bring the system, and I will run the next gate, and I will not simplify. And what do we get? So we get these, right? So that's and now ideally I'd want to factor the qubit. So what I'd want to do is I want to say factor qubits and kind of give it qubit 0. But that's breaking. Oh, factor qubits. Factor qubits. But that's breaking because of there's some phase work to be done and stuff like this, right? Ideally, what you want to do is I want to basically end up kind of here, right? Because the X gate hasn't changed. What I want to end up with is here, but flipped. That that this coefficient is now in front of the 0 and that this coefficient now is in front of the 1. So that's probably a small enough example to play with the factoring. Because I have my doubts about whether this whole phase work is really needed now that I have just rule-based implement. The reason I had the reason if you go to factor qubits, like I could actually have a so the reason the reason these works and here there's nothing about state, so that's all cool, right? That's just reusable. It's the recursive factoring. So measured qubits, blah, measurement. Oh, measurement. It's going to be another refactoring, another big refactoring. So, but yeah, that's cool. So the factorization also kind of needs a bit of a review anyway. So I was just thinking that the factor recursive is, so the amplitudes are built in here with the amplitudes of the edges, the coefficients, which in this case are expressions, right? Mm. And M, which kind of, I should clean that up a lot. So M has the actual states, which are also expressions now. So what factor recursive does is, it stops if get to step 0 and whatnot, and then it basically what it does is it gets a two edges and it just does one run. It tries to it gets one edge and it tries to merge it once with whatever, well, by comparing it to all the other ones, right? And this merging includes, of course, correcting for phases, and then doing this kind of magic trick here with with the how to calculate the oh god the actual, yeah, so you see there's normalization here involved, and then it does this thing where you need to calculate the amplitude of the new of the new merged branch. That's what's going to be complicated. So how do we go about it? First of all, do we need global phase stuff? Let's think about these. So our gates, all they do is they match cat expressions now and replace them with other cat expressions. Now, you have the Hadamard gate, for example, that will replace you things like these, right? But I can also have I can also have a fucker who just goes and says, "Oh, you know what? I'm gonna, I'm gonna do like these, right? So I'm gonna, like, because it will. I mean, you don't have to be a fucker. I mean, it just if you think about it, there might gates that there will be gates that they will introduce a global phase. So I do need to do that because if I don't do that, then the state equals function won't work. Here, because we're dealing with multiple qubits, we need to actually get the cumulative phase. So it gets the global phase. Jesus, how did I do all that stuff? Like it gets the global phase. Uh, where is that? before addition. Jesus. Wow. Uh, okay, so it gets the global phase of each qubit separately. Like that definitely needs some big testing. Like uh, just because I don't know, big time testing. But anyway, so it gets the global phase, and then to each qubit before addition. Why adding it though? I would expect that subtracting it makes more sense. Mm -hmm. And that is the problem. The problem is that, this might be a symbol. That's the problem. Like when I have a symbol, right? eh, like I don't care what the phase is because, well, that's the easy bit, right? Because, it's just a symbol. So if I only care if the symbol is going to be the same. I'm going to assume that if the symbol is different, then we have different uh, qubit states. I can't break that down farther. So I do have to assume that if it's a symbol, if it's not a number, if it's a symbol, because does this work if I just say symbolic false? Yeah, that seems like it works. What? Yeah, that seems like it actually works. Hmm. Why? There's no need to split, of course. Of course. But if I start with a Hadamard, just let me try one thing. If I run a Hadamard gate first, okay, that still breaks because I have these two things and I still want to merge these things, but it doesn't know how. So I have the amplitudes in here, but these are still expressions, of course, and they should be mapped to complex numbers. Like that's like these, right? And then it gets separated. So after the Hadamard, the NOT gate separates it. Okay. What is the best way to design these? First of all, if it's what if it's a mixture, right? What if it's a fucking mixture? Oh God. What if it's a fucking mixture? So it seems like I need to just be able to, like the whole thing, I'm assuming it works. So what I have to do is I have to figure out what do I need to do if the state that I have at hand is a symbol or is not a symbol. If it's not a symbol, I should be able to translate it into an actual complex number. If it's a symbol, then it should still be a symbol. And I probably should do this in the previous function, in the actual factor qubits. When I prepare both the amplitudes, because I know I've designed it this way that now you kind of initialize everything symbolically, but ideally, I'm thinking another thing that would be cool is that you kind of can have something partially symbolic, like especially to do the teleportation case, you'd have a couple of qubits. You have one qubit that's just not symbolic because it's known, it's a Bell state, blah blah blah, and then but then you have your initial state as being a symbolic state, like a generic symbolic state. So so you want to have mixtures of both. So we're going to have to embrace these. So both at this point, right? So both at this point and at this point state, right? I have to make sure that I translate the stuff into either symbols or NumPy complex numbers, because if I translate it to NumPy complex numbers, then I know that this stuff works because it used to work. The problem is maybe that's not the place, because the problem is, I want to keep it, I want to keep the whole thing being an expression all the time, right? Like in factor recursive, what do I do here? What can I? There you go. I wouldn't. What would happen if I get rid of the global phases stuff first? So for example, I say blah 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 blah. This is all good. This is all good. So just give me a second. Gotta open the door. This back there. Cool. Um, where was I? So yeah. So if we get rid of these, maybe it'll work. So I'm getting rid of these, and anything that is, assuming I'm going to assume everything's equal. Measure qubits, I'm gonna get rid of these. And then what do we have here? So then we're normalizing. What are we normalizing? Oh, we're adding them. Incorrect local. I don't remember what I did here and why does this matter. But oh, it's adding the global phases, and so what you're pinning at the end is just the state. Okay, so what I should do instead is have just have these here. I just want to try. The only thing that I want to try is if it works, because now I have that sucks, right? Because here we're doing NP stuff, which is where I'm reshaping. I'm basically doing transpose shit now. Doing transpose stuff in here, and I'm saying, yeah, because it's a complex, because it's a state, so it's a complex array. And so what I want to do, I just don't remember how I did that, but I remember that I did the math, and then if I reshape these and then I reshape that, then like I was coming out with the amplitude being the dot product between all this stuff. Oh. We'll have to figure that out again. So what about that stays here? What about we comment that out? So we ignore these. Oh, come on. The battery of the mouse is dying. No, don't do this to me right now. Yeah, awesome. So we'll have to use the track pad or just the key. Come on. Oh God. This is being well prepared. Yeah, it doesn't work. Whatever. We'll have to live with these for the moment. So what about the correct phase? We must take the state without global phases. We assumed we've corrected it accordingly. If merging is not successful, the global phase shouldn't be altered. So here, so far again, I'll just leave these. These almost will require, I think, a re-implementation. So what we've done so far, so I've commented out everything about phases, got the states, calculated the normalized stuff, and then I just basically, I'm gonna go ahead and say, this is the only one, there's the nodes, so what's the amplitude? Because I remember what I was doing is to calculate that I was trying to make sure that this amplitude would allow me to recover the state. Let's just say 1 for now. Let's see. I just want to know whether the whole thing runs through. Yeah, and then we're just calling this whole thing again. Cool. So if I will clear and restart the output. Will this work at all? What are we trying to do here? Okay. No, it broke. Where? Cat object is not iterable. So where is this happening? 463. There's some global phase I'm missing, I think. 400 factor phases. Where is that? Is it factor qubit? Oh, it's a preprocessing. It's in factor qubits. So factor qubits. Yeah, there you go. So huh. Oh, so make sure all node global phases are bubble tapped to the corresponding edges. Yeah, okay, but that's needed, but still I need to account for the stuff while merging because I might merge things in a way that that signs will just squeeze in down there. So that's not a solution to all my problems at the moment. So we'll clear the output and see what's going on. Cool. So let's see what happens. Broke. Yeah. Okay, so there's still. Oh, the normalize. Yeah, that's definitely. That's definitely. I didn't I change that? So a factor rec. Oh, what am I doing? I'm writing here. God. Factor recursive. So we should go. Yeah. That shouldn't be these. That should be just these. So what I should do is I should just do nodes n equals these. This is all I should do. And now restart. Because we don't want, this is gonna, yeah, normalizing won't just work. Because it was assuming that the whole thing is an NumPy array. Okay, cool. So it's there. Oh, what am I doing? What am I doing? Cool. Let's see. Hopefully. Oh, Jesus Christ! Just copy shit in here. Look at these. That worked out. Okay. It worked out for. Yeah, it worked out. So as you can see here at the bottom, I'm back at these. So now the question is, will this work out for symbolic stuff? Like if I just say symbolic true, that would be awesome because this means that oh yes, look at this. That has worked. So we basically have the coefficient of n5 underscore 1, which was, accompanying the 1, it's now the 0. And yeah. So basically that has, cool, that works. Could I hardcode like a mixture of these? It's a bit stupid, right? Because if I know one coefficient, I should know the other. But if I go to, if I go here, and I just cheat a little bit and say, no, I should go to the, there I go. Here, instead of symbolic, what I will do is, I want to cheat a little bit, and then comment this line and then say, look, for the ket one, we will start with a square root of 2 I know that, that would imply that I know what the other coefficient is, but I just want to know whether mechanically that works, from a code perspective. Because then it means that I only have to worry about the how do I do the factoring stuff, how do I do the phase stuff, right? Because it's going to be I'm going to have a mixture of symbols and numbers, and I really don't know how I would approach that. See if that works. No, SQRT is not defined. Oh, my fault. Because it's from SymPy. What is it doing here? So, there we go. Let's see. Let's hope that works. At least that it doesn't break. Okay, that's not bad. Actually, that worked, right? Because the square root of 2 divided by 2 coefficient was in the 1, and now it's in the 0, and then that's there. So, okay, yeah, it looks like it works. Now, there are two things which are not working here, right? Or two things that now I have to figure out how to fix, how to refactor. One thing is the calculation of the amplitude of the merged. No. There you go. So one thing is of course, all the phase stuff, and the other thing is this part here, the normalization part. So three things: the normalization part, and then the calculation of the new amplitude, because now I have these complex numbers which are coefficients of the kets elements in the expressions. I still like the expression is still valid, right? So I guess what the reshape is doing, I probably should go and do the math again. Oh, actually, I don't have a mouse, but I do have the pen, so I could use the pen. But I cannot switch between these screens. Whatever. Never mind. Oh God, that's complicated. Let's think about the phases first. I need to do that. Because. But how do I do that? Do I want to translate the do I want to translate the states into NumPy complex arrays and then back into states, into expressions? Do I want to do that? I probably have to. It sucks, but I probably have to. And I think I have to do. If anywhere, I should do that at the very end of where all these phase functions are. So yeah. And the same with normalizing, right? So I should take a look at what the expression here is telling me. And what am I doing with normalization? So normalize edge amplitudes. No, that's not. Factor rec cursive. This is called normalize a complex array function. Yeah, so what I should do is I should probably calculate the norm of these. Like I should do this with SymPy. Like can I even do this with SymPy? There's too many things. It's just too many things in my head right now. God, I'm a bit overwhelmed. Because in SymPy, with SymPy, you work with expressions, and I'm not an expert at all in SymPy at all. But how would I go about this, right? So I have a bunch of symbols, and then I would just calculate the norm. Yeah, it would just probably generate the norm as an expression, which is really what I want, right? Either that or so. Let's check. Let's check out. So SymPy, um, SymPy calculate norm. Norm of complex numbers. Give me a second. Okay, back here. Someone was at the door again. So calculate norm. So complex values, numerical evaluation, elementary, I don't know. God, it's a pain that I run out of battery. Oh, look at this. Got some extra battery left. Hopefully that will work for some minutes still. Yeah, it's gone. I don't even know what I'm trying to do. If I go to complex numbers, this doesn't even seem to be about complex numbers, is it? Is this about complex numbers at all? Why? That's weird. Complex. There we go. So I have it. I get the norm, and then I divide the array and all that stuff, right? That's fine. But I how can I do that with SymPy other than getting all the values myself? SymPy calculate norm of array. It's probably there's a bit about matrices in here. Normal vector using some Stack Overflow. So I need to calculate the norm of a vector using SymPy and symbol from SymPy and extract the codes below. So what this person is trying to do is create a symbol and then an expression. What? I have no idea what is this doing. SymPy has a vector module you can use. You can also use it with symbols. Oh, okay. So symbol XYZ vector dot v. Ah, interesting. What is C? What is C? Coordinate system 3D. What? What the hell? Reference frame. What is these? So it has physics of vector. Reference frame M. Doesn't look like there's a nice, easy way to do that. Vector. So returns the components of this vector. But this is coordinate system 3D. That's it for 3-dimension vectors, and that's not what I want. I mean, I might as well just get all the values, right? One by one. I might as well matrices. I don't want matrices, but there was something about complex numbers in here somewhere. I don't want matrices. What I'm trying to find is I'm trying to find how to just calculate that is if I have an array of these values, I should just probably what I should probably just do is get all the values out. But I mean, what is the norm of? I have absolutely no idea. That's definitely going to be for the next session then. But it's basically the to-do that I have. So I have to figure out how to get these done with SymPy. That'll be my next big step. Hopefully I can get to it tomorrow with batteries on the mouse. And yeah. Blah. Where was I? So dev factor. There we go. So the to-dos are all this kind of stuff. The global, because the global phases are I think there still is. I think here I could just still take the complex number, turn it into an array, turn it into a NumPy array, and get the relative phases stuff out. Unless, yeah, because I don't want to, yeah, and if it's a symbol, I would just leave it untouched, right? So here what I would do is, for example, yeah, get global phase would only work for actual complex numbers. Um, uh, factor phases. So what am I doing? So actually in here, get the global phase. Yeah, that only would work if the number, yeah, to be honest, I'm thinking now that I think the only places need to change that is in the R to P, and you know, because these are the only ones where I actually get that. So here I probably have to do convert expression, or convert the expression to NP array of complex numbers, and the same here, right? If I get this done, expression, I mean, that is a number, actually. That is literally a state. No, actually, that's easy, right? Because I have, that should be easy because, and here I don't have to, this one, no, this I don't have to. What I do have to convert the result below to an expression. This is what I should probably do next time. Because this would allow me to say, cool, so for the stuff that it's an actual complex number, let me turn it into NumPy, then do the actual math, and then put it back into the expression. And if it's symbol, I'll leave it untouched. Can I do that? So convert expression to unpay. Yeah. So this should be easy, right? Because what I should do here is, and I don't know if I should not. Here's the assumption, right? So expression state. So what I should do here is I should basically get a, a cat 0 would basically be x coefficients of SPQ cat 0. So I get the coefficient of cat 0. Here I get the coefficient of cat 1. And somehow NPX would be basically an NP array of cat 0 and cat 1 of D-type NP complex, and then all I want to do is those things in NPX and NPX. So this is probably what I want to do, and what I want to do here is probably have the result. The NP result is in here. No, what am I doing? Oh yeah, exactly. And now I probably need to just return an expression that is basically NPR. Oh. Oh, the other way around. What am I doing? No, that's correct. This Cartesian to and yeah, now in here I have the Cartesian one. So what I want to do is I want to say NPR. Do I want to really do these and say real plus NPR one, no, 0 Emac plus so all these times SPQ get 0, and then so that will be the expression, right? And then do the same for kit1. Yeah, I think this could work. Actually, let's try it quickly. Let's do a quick test. Is P2R, actually, I just ran out of time. Anyway, sorry if you're following, actually. I'll really try to, kind of dial in tomorrow, do a bit of a follow-up stream on these and test the stuff. But I think that is about right, without having tested it, of course. But I think that's about right. And then I just need to figure out how to do the norm thing, to kind of do the normalization stuff. And it's like there should be a way to do that directly with SymPy, because if I have an expression and I just want to normalize the coefficients, but it's really quantum specific, and I don't think if SymPy is able to recognize that. So that would be one point, and then the second point is the calculation of the target amplitude for the new edge. So that would be the next thing to do. But yeah, so it's going to be a bit tricky. I think the next couple hours will be a bit tricky, but if we get that right, then the factoring will work with a mixture of symbolic and non-symbolic states, and that's already a big plus. And then we'll only need to take a look at the measurement and post selection, and then we'll be done, I guess. Then we can focus on visualization and just getting some proper testing out. But I think that's basically it. So I gotta run, and wishing everyone a good day.